So I'm sending home the litmus paper with you guys, right? Because we're not going to meet in class for the next 2 weeks. Well, now next week we're out just because it's our normal break, right? But I'm going to be out of town the following week, and so what I'm going to do is record the lecture, and I'm going to let you do the lab at home with the litmus paper. It's a very simple lab. You're just basically identifying. There's common household items. It's a lab 11.1 in the book, and you're just going to use the litmus paper to determine whether or not these common household items are acids or bases. Okay. So what I've done is I've given you 8 pieces of litmus paper, and so there's probably about 14 in the lab, 12 to 14 items that they say that you can do. So just pick 8 out of the list. I don't care which 8 you pick, but pick 8 based on what you have in the house. What I'm trying to keep from you having to do is go out and buy something that you don't have, right? So just pick 8 items that you know you have around the house and test those out, and then write up your lab report based on those 8 items. Okay? Is that clear to everybody? Yeah? Okay, so basically all of Ian is out next week, but other kids will be coming back for classes on the 25th, and so we're not going to be in class, but what will be due on the 25th is your test, which I handed out to you. Everybody got a test? Everybody get one? Okay. Do you have one? I thought I put one over there, did I not? Okay, it's not. No, it wasn't in the folder. I thought it was Michaela's paper that I sat down thinking that was an empty test. So if you'll put that in your folder. All right, so you're going to go ahead. You don't have to do this, right? You don't actually have to turn in your physical test until March the 4th, which is the first day we're going to all be back together, Lord willing. But I would recommend going ahead and taking your test right away, because you're going to do like 2 sections in chapter 11, and you're going to totally forget, chapter 10, because it's not really related at all. So I'd recommend going ahead and doing your test. Go ahead and reading those, and then reading your pages and doing your homework. So this technically is due the 25th, but you're not actually going to hand it in until the 4th, which is the day that we'll be back in class. And so due that day will also be your lab report that you're going to do at home, where you're testing the 8 substances. And basically all of the homework for chapter 11 will be due that day. You'll need to study for the quiz, which is just going to cover the portion of the second half of chapter 11. And I'll hand out the chapter 11 test that day as well for you to take home. Okay? So is that clear to everybody? No class next week, no class the week afterwards. Everything, you don't have to turn in anything, you don't have to email anything to me. You don't have to email your test to me or turn it in online. Just bring the physical copy, completed copy back on 3/4, and that's when I'll take those home and grade them. Okay? Because I'm planning to be skiing and I'm not planning to be doing any grading. All right? Not skiing technically, snowboarding.
That's way better.
Way cooler. Way cooler. Make sure you guys tell Joshy that. All right?
Oh, I told him.
Snowboarding is way cooler than skiing. All right. All right. Did we have enough litmus paper?
No, we got 5.
Got 8 of each? Okay. Have you guys already got yours, Michaela? Okay. So yeah, Jimmy, just have those back. Are those bottles in? Okay, you can throw those away. Yeah, thank you. All right. So let's see what we got for chapter 11 today. Everybody say out loud, "Thank you, Lily."
I know, I'm so sorry for spoiling.
Let's hear it. Thank you, Lily. For those that are watching the video on the camera, Lily asked me to work the exact problem, which turned out to be the problem on the quiz. So we did that just before the quiz, so this class was well prepared for the quiz. But that's why I give you guys time to ask questions at the beginning of class, and if you happen to ask the right one, then you just got a lot of help on the quiz. All right, so let's look at the characteristics of acids and bases. That's what we want to talk about today, is acids and bases. That's what you're going to be checking in your experiment. You're going to find out that you've got plenty of household items, chemicals in your house that qualify as acids or bases. And so what are some characteristics? Let's talk about the characteristics of acids and bases. Starting with acids. So I want you to know that solutions with an acid are called acidic. All All right, so if we say we have an acidic solution, it means that it contains an acid in it. So who can give me, so we got three characteristics that I want to highlight as far as acids, and the first has to do with the taste of acids. Does anybody know how acids typically taste?
They're sour.
They're sour. Acids are sour. Tend to taste sour. All right, and so the easiest way to me to remember that is you've probably all heard of citric acid, and citric acid is what you find in citrus fruit, right? And like oranges and grapefruits and things like that, and they can be sour, right? So that'll help you remember that acids tend to taste sour. Second characteristics is that acids are what we call covalent electrolytes. And we'll explain in a little bit why that is the case. But what that means is that they conduct when dissolved in water. All right? So acids conduct electricity when dissolved in water. And then what you're going to discover at home is that, and you've probably already done this in physical science or some other science, but they turn blue litmus paper red. All right. And so just while we're on the topic, what is litmus? Litmus is a chemical that changes color in presence of an acid or a base. And so in the case of an acid, your blue litmus paper will turn red if you get an acid on it. And the way that I remember that is that, you know, anytime you see like acids in a movie, usually if they pour acid on something, it like smokes, like it's eating through it, you know, and getting really hot and all that. So I just think of something being on fire, like red, you know, fiery red. And so that's how I remember that it turns blue litmus paper red. Even though notice that's not in any of our characteristics that acids like, you know, eat through things. Let me give you a definition for an indicator. An indicator just in general is a chemical that undergoes a distinct, observable change when the conditions in its solution change. And so that's a general definition for indicator. Litmus is a specific indicator. Litmus is an indicator. So there are other ways that indicators work, not just simply changing color, but litmus, that the distinct observable change that takes place in litmus with your litmus paper is that it changes color, right? So litmus is an indicator. But that's what an indicator is in general. So now let's talk about bases and consider three characteristics of bases. And by the way, a solutions with a base are called, does anybody know? Basic. Or, anybody know the other word? You see it on some batteries, yes?
Is it alkaline?
Alkaline, yep. Basic or alkaline. Very good. Did I spell your name right, Michaela? Mikayla. Yep. And so how do bases taste?
Bitter.
Bitter. Tend to taste bitter. Think of coffee. Coffee has a base in it, and so it gives it its bitter flavor. That's why is it EI or IE? Well, I ask that like every time, right? I always write it right, and I'm
No,
like,
you have never. This is the first time I've ever learned you keep writing right, and then all of a sudden you're like, wait,
You've always wrote it correctly.
I have?
Yes.
Yeah, I don't know why, right? It's like all of a sudden, well, it's like Michaela's name. I can't, it's because I'm thinking about snowboarding. I'm just so excited about going snowboarding, right? So they tend to taste bitter. And that's why I think coffee always requires like some cream and a little bit of sweetener in it, because it's just too bitter to drink black. I think people that enjoy black coffee, something happened, you know, their taste buds they've killed their taste buds or something.
I drink black.
Someone did in the last class as well. But yeah, I've tried, and I'm sorry, I just can't do it. It's like, I'd just rather give up coffee if I have to drink it black. I'm not like my son Joshua, though. We found a sign when we were at Hobby Lobby, and it said, I like a little coffee with my creamer. And that's definitely Joshua.
That used to be me.
Really?
My taste buds just changed.
Really? So you didn't like try to like steadily take it down and make them
No,
change?
I went from heavy creamer to none at all.
Really? Wow, that's weird. I'm telling you, you destroyed your taste buds somehow. your base indicators have been damaged. All right, so bases are also slippery when mixed with water. Most soaps are bases. The bar soaps are bases, so that makes sense, right? You get a bar of soap wet, you can hardly hang on to it. And then they also turn red litmus paper blue. All right, so those are our three characteristics with being able to physically identify acids and bases. All right, any questions about those characteristics?
I have a question. What would an acid do to a red litmus paper?
Nothing. So yeah, so when you test the items at home with the red litmus paper that are acidic, it's just going to stay red. I mean, it'll be a little darker because it got wet, but it's not gonna change color. All right. Okay. Chemical this is just superficial definitions of acids and bases, but we're not superficial people, right? We're chemists. Okay, so we're going to dig in and we're going to find out chemically why is this an acid and base, right? Let's look at the chemical difference between acids and bases. All right, so let's talk about this compound. Can anybody tell me what this compound would be named? Or what it is named? Hydrofluoric acid. Wow.
Don't give me an extra point. It was right in the book.
Oh, does it? Okay. I was like, that's almost worth an extra point, that she would just know that. Okay. All right, an extra point for your honesty. All right. All right. Does anybody know what it would be named based on the naming conventions that we've learned? What kind of compound is this? Is it covalent or ionic? Is it?
It's covalent because they're sharing.
It's covalent, right? They're sharing the electrons. If this was a metal and this was a non-metal, right? We got to have a metal in there. So this is a covalent compound, so we're going to be using those prefixes that we learned, right? And we use the prefixes on the front as well, unless it's one, right? In this case, it is just one hydrogen. So this would be hydrogen monofluoride, okay? Just a little refresher in the naming convention of covalent compounds, all right? So if we have hydrogen monofluoride, commonly called hydrofluoric acid, and we take, well, I don't need to rewrite it, I'll just do it up there. So fluorine is, if you guys remember when we learned about electronegativity, what is electronegativity? It's how strongly an atom attracts in this covalent bond. It's how strongly it attracts the electron, right? So the more electronegative, the more strongly it's going to pull on the electron. And so as it turns out, fluorine, I don't know if you remember, but fluorine's like over there in the top right side of our periodic table. No, wait a minute. It's in the top. Yes, the top right side, but not in the inert gases, right? Not in the noble gases. So it's the top right if you exclude the noble gases. And we said it's the most electronegative, right? So it's really not sharing its electrons fairly at all with the hydrogen atom. The fluorine atom attracts it much stronger. So what happens is that when you have H2O, the hydrogen atom, because fluorine is being so stingy with its electron, the hydrogen atom's like, I want to go over here where they're sharing, they're a little nicer, right? So the hydrogen atom ends up coming over here. But when it does so, because the fluorine is so electronegative, the fluorine's like, well, you're not taking your electron with you, right? So the hydrogen atom just goes over there and leaves its electron. Now, do you guys remember with the hydrogen atom how many protons and neutrons and electrons it has? How do we determine the number of protons in hydrogen? How do we determine the number of protons in any element? By its atomic number, right? Exactly. We look at the atomic number on the periodic chart and we see that hydrogen has an atomic number of 1. So that means hydrogen has 1 proton. And anytime we know the number of protons, we also know the number of electrons. So it has 1 proton and 1 electron. And hydrogen is kind of unique compared to the other elements because it doesn't have any neutrons. Right? I don't know if you guys remember learning that, but we did, so trust me. All right? So if it's going to leave its electron behind and go over here to the water molecule.
It leaves it with fluorine?
What's that?
It leaves it with fluorine?
It leaves what?
It leaves it with fluorine.
Fluorine, yeah. It leaves the electron over here. So what happens, what's actually coming over here is an H plus hydrogen ion. Okay? It got rid of its 1 electron. So really what this is just a single proton. Right? Because it only had 1 electron to begin with and it just lost it. So that single proton goes over there. And so what you get is you get a fluorine ion that's formed with a 1 negative charge. And you get this molecule, this ion, which is what we call the hydronium ion. So the hydrogen left fluorine, went over here, connected to the water where it could get a more fair share of the electrons there. And because it came over as a single proton, when it left the fluorine became negatively charged. And when it joined itself to the water molecule had a positive 1 charge because now it's got an extra proton, right, compared to what it had before. And this is just a common ion formed in these types of reactions. So we give it a special name. The hydronium ion has a 1 plus charge. So this is technically what is happening every time an acid-base reaction takes place. Acids and bases those reactions always go together. If an acid is reacting, you got to have something that's functioning as the base. Okay? And so if we write this down without the dots, the reaction looks like this. And so what happened in this case is that hydrogen monofluoride, or hydrofluoric acid, right, donated the H+, and that makes it the acid, because it got rid of the hydrogen ion, and the water received the hydrogen ion, and so that makes it the base. And so technically, the definition then of an acid is this is a chemical that donates and H plus ion. This has been a great day to have donuts in class because we're talking about donates, and it's such a close word, it's making me want a donut. Man, if only I'd thought of that. This COVID just messes everything up. You know, you don't think about bringing food anymore. All right, proton. So what we said though with this H plus ion is it's just a single proton, right? So we call an acid, it's also referred to as a proton donor. It's donating a proton to the base. And that's what a base is. A base, by definition, is a chemical that accepts an H plus ion. So it's a proton acceptor.
I have a question.
Yes.
So so do all acids and bases have hydrogen in them then? If they like donate and accept the
Well,
ion?
so it will the acid will always have a hydrogen because it's by definition has to donate that hydrogen, right? So to start with, the base may not, but it's going to end up, that base is going to end up with a hydrogen, right? And so we'll see some reactions where there's not necessarily the hydrogen to start with in the base, but it will. That's how we know that it is the base, because it's going to end up with a hydrogen, with the hydrogen ion. All right, so let's see. So we can see by this reaction here, this is why acids are covalent electrons, because when it donates the hydrogen, you're left with these ions, and then what do we have to have in order to conduct electricity? We got to have these ions that can freely move in the solution, right? So since we've got ions on the other side here, that's why they're called covalent electrolytes. They conduct electricity when dissolved in a solution. All right, so let's look at any other questions before we look at another reaction? All right, let's consider this reaction. NH3 plus H2O gives NH4 plus OH negative. Now, if we think about our technical definition for an acid and a base, and we can handle a technical definition because we're all chemists here, right? So a chemical that donates the H plus is the acid, and the one that accepts it is the base. So if that's the case, in this reaction here, which one is our acid and which one's our base? The water is the acid this time. She's exactly right. Because it got rid of an H here and made this OH on the other side, right? And we can see clearly that this is the base because it only had 3 H's before, and now it's got a 4th H, and it's got that positive 1 charge. So it must have got the H plus ion, the single proton, right? And this must have gotten rid of it because now it's carrying a negative charge because it's missing a proton. All right, so can everybody see that from looking at this? This should be pretty obvious in this reaction. The reason that I wanted to show you this is because here the water is a base, but in this reaction the water is an acid. So you can't always just look at it and say, well, I know that chemical behaves like a base in this reaction, so it's got to be a base in the next reaction. Some substances, that's true for some substances, they'll kind of always be one or the other. But other substances, they can function as a base in one reaction and then form as an acid in another, okay? So we have a special name for that, and we call those substances, I can spell it correctly, amphoteric. Amphoteric. You may also see it written as amphiprotic. And this is basically chemicals. These are chemicals capable of of reacting as an acid or base. Now Jerry was asking, do you have to always have an H in the acid and in the base? And I said, not always in the base, but if it's an amphoteric substance, it's going to have to always have an H in it, right? Because if it's going to function as an acid, sometimes it's got to have some hydrogen ions that it can give up. All right, any questions so far? I'm 32. I know you guys are all wondering. Is that what your question was? You're like, no way, dude. You're living in a dream world. All right. No. All right. I am going to be 50 this year, so my birthday's coming up. Just so you guys will know what to get me. You got a few months to think about it. It's not till late June. So, all right. All right. Cool. All right. So acids. Let's talk about acids and ionic bases. There are covalent bases. Here's one right here. Right? Does anybody know what that is, by the way? NH3? That's a common household chemical. Ammonia. Yes. All right, Elizabeth's kind of, man, I don't normally do this, but she's answered a lot today. So I'm just feeling generous, I guess, because we're going skiing. So, yes.
What is ammonia?
What is ammonia?
Yeah, I've heard it before, but I don't know exactly what it is.
Oh, like what chemical it is? So it's used in window cleaners a lot. So Windex uses ammonia. It's got a very distinct smell to it, in fact, you can use straight ammonia for your windows, but Windex definitely has it in it, so it's great for that. Off the top of my head, I don't remember what other things it's useful for. I always think of window cleaner, but it's definitely a window cleaner. So one of the things probably on your list of items to test is probably window cleaner, right? And what should happen if you put the red strip in the window cleaner? What should happen? If ammonia is a base, then the red one should turn blue, right? If I put the blue one in the window cleaner, it won't do anything.
Wait, what about if, like water? What would happen, like if you put the paper, like if they function as an acid and a base, then what color is the paper?
Oh, right. So it's going to generally be in a solution that, I see what you're saying. So like, what if it's one or the other? It would just depend on the solution, whether it's functioning as an acid or a base in that particular solution. But yeah, in the case of water, well, you're going to do water. Let's see what happens with water when you test it at home. So make that one of your 8, okay? And we'll talk about that next time.
Is there a bunch to choose from? Like, do you think there would be a lot of cleaning products in the options?
There are several, yes. Yeah.
Because
You would expect that, wouldn't you?
yes.
Yes, okay.
But except my mom, she's like very organic and green.
Right, so you may not have the one that it's asking for. And that's why I said only 8, because you got like 14 to choose from. So some things are like juice,
Okay. That should
and
be
water, and soap, if you've got detergent. So, I think there'll be enough milk, there'll be enough in there that you'll have 8 to choose from. All right, cool. Okay, acids and ionic bases. So there are covalent bases like NH3, and NH3 basically always functions as a base. Basically functions as a base. You see what I did there? I didn't even mean to do it. I'm just that clever. It's just automatic. All right, so we should recognize ammonia as a base, but so our polyatomic ions. Remember our polyatomic ion chart on page 245, I think it is. I said there were 7 polyatomic ions, and I said you guys needed to memorize, and I was gonna hold you to that. And you were gonna have a quiz, and I was gonna test you on it, and then we didn't do it, right? So I knocked it down to 2 because I'm such a nice guy, and you only had to remember 2 for the last test. But some of you didn't even remember the 2 that I told you to remember. But anyway, that's another story. So from now on, even though I wanted you to memorize that initially, I'm not going to make you remember that going forward. Okay? So if you need it on a test, like the next test, or maybe the next quiz, I'm going to put it at the top of the test. Okay, so you'll have that chart with the polyatomic ions, but it's still good to go through the exercise of just trying to remember those so that you'll quickly recognize them in a substance. Okay, I want you to be able to pick out those polyatomic ions. So that's going to be really important when you talk about acid-base reactions. All right, so let's look at this reaction for example. HCl aqueous plus NaOH aqueous, H2O as a liquid plus NaCl, which is aqueous. And so in this equation here, this is our acid, this is our base. And so you should recognize a polyatomic ion in here. Does anybody recognize the polyatomic ion in this reaction? OH. IO. That's a Reliant K song. They're from Ohio. So OH is the polyatomic ion. OH, does anybody remember the charge on OH? Negative. Does anybody know the name of OH?
Hydroxide.
It's a hydroxide. Man, all these smart people. You guys are making me so proud. All right, so hydroxide ion. That one should have been the one that was clear. I'm just feeling so generous. I'm just feeling the love today. So let's write this down. Let's kind of break it up. Now that we know this will split into an ion, let's write it down like that. Split it into an ion. So HCl aqueous plus Na plus aqueous. Right. So we're going to split this guy apart into its ions. And so OH has a negative charge. Na is in column 1. It's going to have a one positive charge. And so OH negative aqueous. And then on this side, we have H2O. And we've got another ionic compound on the right side as well. So we're going to split it apart into its ions as well. Check it out. So we've got Na plus aqueous over here. And then we got Cl minus aqueous, which is our ionic compound on that side. All right, so now if we write it this way, splitting it apart into the ions, now it should be really obvious which one is the proton donor, right? The proton donator. I like to say it that way because, again, I like to think the donuts. But the one that donates the proton is clearly got to be what? It's got to be the HCl here, right? Because this OH took that H and became H2O, right? So the HCl was the one that donated it, and the NaOH was the one that accepted it and became H2O. So can you guys kind of see that as we split it up, how it makes sense that the H that was donated came from here? Right? It wouldn't make sense that the H came from here because what's it going to go with and somehow form the only compound on the other side that's got H? It clearly came from here and went to this. And also, since if it went over here to this, what's going to happen? It went as just H plus. So it makes sense then that the H plus combined with the OH negative now has a neutral charge on H2O. And it makes sense that the Cl had a minus charge on it over here. And so therefore it combined together with the Na, which had a single positive charge. Right? So everybody's happy. So everybody see that? Right? Which one was clearly the acid and which one was the base? Now notice when we split it apart into the ions, on this side here you have HCl, and you don't have HCl on the other side. You have OH. You don't have OH by itself on the other side. But Na plus, we've got Na plus on the left side and we've got Na plus on the right side. So it didn't. The point with the Na plus is it really didn't participate in the chemical reaction. The focus of the chemical reaction in this was the donating of that hydrogen ion. And Na plus wasn't involved in that. So Na plus is what we call a spectator ion. Just sits on the sidelines, it's not in the game, it's just spectator. All right? So Na plus spectator ion doesn't participate in reaction. All right, so let's do an example. Let's do example 11.1, page 333. And example 11.1 says, asks us to identify the acid and the base in this problem. MgOH IO. Here we go, guys. Here we go. 2HNO3. MgNO3 2 aqueous plus 2H2O. Okay. So which one is the base and which one is the acid? So we're going to do the same exercise that we just did here, where if we see an ionic compound, we're going to split it apart into its ions and see if we can tell which is which. All right? So we have an ionic compound right here because we have a metal combined with a polyatomic ion, OH. And so Mg is in column 2 on the periodic table. It carries a 2+ charge. So we got Mg2+ aqueous here plus OH aqueous here. Plus 2HNO3, that's not ionic. Here again, Mg2+, it's aqueous, plus NO3, which carries a negative charge, aqueous, plus 2H2O as a liquid.
Would the OH have a negative charge on the left
Yeah,
side?
would that have a negative charge? And we need to put the 2's here. Because we got 2 NO3's and we got 2 OH's there. Okay. So I didn't overlook anything. Thank you for pointing that out. So now that we've written it like this and separated out the ions, we should be able to tell, since we just learned about spectator ions, that Mg2+ is like that in this chemical equation. It's just hanging out, right? It's the same on the left as it is on the right, so it didn't really directly participate in the reaction. So these are really the two that we're focused on. And so we can see based on this that the OH, again, like we saw in the last problem down here, the OH received an H from HNO3 and became H2O, right? So OH became H2O. It received the hydrogen that was donated. So HNO3 donated the hydrogen. So we're going to call this then the acid, right? Because it gave up a hydrogen ion. And the MgOH was the compound that received it because it split apart and this OH received it and became H2O. So this is the base in this reaction. Everybody see the thought process that we went through to figure that out? All right, let me say this. Some of you definitely aren't getting it whenever I ask that question because I could tell that based on the last test. So if you really don't understand it, let me know that you don't understand it. If you don't want to ask in class, then ask me after class, all right? Or come before class and ask me about these things because I'm here to help you guys. All right? It's like Christ saying, come unto me, all you that labor and heavy laden, I'll give you rest. You got to come, right? You got to come and ask. You got to seek. Seek and you'll find. So if you want to know, if you want to understand, come see me. And we'll make sure that you understand it. Okay? So does everybody get this? And if you don't get it, you can ask me after class, okay? Or you can ask me now. It's okay. Nobody's going to laugh at you. Maybe a little bit, but not a lot. I'm not going to let them laugh at you a lot. No laughing allowed. That's not true. Okay, we'll just move on, all right? No questions. We're going to keep going. We love to laugh in this class. It's like the joke I told you guys last week about why dogs can't fly. Huh? it's still a good one. Still a good one. All right. Okay. Oh, you guys crack me up. All right. So let's recognizing acids, bases from formulas. All right. So, how can we recognize acids and bases just by looking at the formula? There are actually some tricks where you can look at the formula and go, oh, that's probably the acid, that's probably the base. One thing that we can look at is that ionic compounds which contain the hydroxide ion act as bases. And that's exactly the kind of compound that we had in this last problem that we did, as well as the example that we did before that. Right? The one that ended up being the base was an ionic compound right here, and it has the hydroxide ion in it. All right? So that's one thing that we can look out for and kind of easily identify the base. And so if we identify the base, then we can tell what's the acid if it's just two compounds being combined together. Another thing, NH3, ammonia. You can always assume that's a base. It is a covalent base. All right? So whereas these are ionic bases, and how you identify the ionic bases, if you see NH3, that's going to be a covalent base. That's always going to be your base. And then finally, if a covalent compound starts with H, often acts as an acid. So a good assumption to make is if you've got a covalent compound that begins with H, and it doesn't have to just be one H, it could be H2 or H3, then that will usually be your acid. Okay? And sometimes you'll even see that the H's are split apart and the compound's written in such a way that it emphasizes how many H pluses that the acid donates. And so that's an important point. Let me define what we call a polyprotic acid. Polyprotic acid is an acid that donates two or more H plus ions. Donates, let's see, acid, well, I'll just say donates, I already called it an acid, donates two or more H plus ions. Now that being said, even though we have some acids that can donate more than one H plus ion for this class, assume each base can only receive one H plus ion. So even though we will have some acids in this class that donate more than one H plus ion, the bases will always only receive one. Okay? And so you'll see why in this next example that's an important, we have to know that that's an assumption that we can make. So let's go ahead and do another example. Any questions about those points or definitions? All right, so example 11.2, which is on page 335, says, what is the chemical equation for the reaction between H2SO4, which is aqueous, and NH3. We know that. What's NH3?
Ammonium.
It's ammonium, and it's always going to be
Base.
a base. Ammonia is always going to be a base. So that's our base, and that's our acid. So we know that going into this, right? And so what's going to happen then? Well, this H2SO4 is going to donate the hydrogens that it has, but it doesn't have only one hydrogen that it can donate. How many is it going to donate? 2 hydrogens, because it's got 2 hydrogens, and actually we should recognize that SO4, it's a polyatomic ion, which Elizabeth has told us very clearly. The name of that ion is sulfate. It's a very strong, assertive statement there, Elizabeth. Here's the sad thing, I'm the chemistry teacher and I'm not sure. But I think that's right. So let's look on page 245 and let's see. Yeah, of course that's right. Yeah. Cha. All right, so SO4 is 2 negative, and so that makes sense that it's going to donate 2 hydrogen, 2 H pluses, right? So that would all balance out charge-wise. All right, so if it's going to donate the H2, so what's going to happen here is then this base is going to become NH4, because remember what we said in our last comment down here. For this class, we should always assume that the base will only accept 1 H plus, right? So we can't let the NH3 have both of those. We're just going to let it have 1. All right. And then what we have over here is just SO4 2 minus, right? Because it got rid of 2 protons, so it's got a 2 minus charge. So that's what's left over. So this is our reaction. Now what we've got to do is balance our equation. All right? Some of you are looking and going like, how does that work? You know, we still got to account for these. Assume all the H's are given away in your acid, but assume that your base can only receive 1. And that's how we figure out what the chemical reaction is. Okay? So now let's balance it out. Well,
Where does the other H go?
well, you'll see that when we balance it, because we have to make sure the number of H's on this side are matched with the number of H's on this side. So basically what's going to happen, since it had 2 H's to give up, but this could only receive 1, then we need to assume there were 2 NH3s. Right? So if we had 2 NH3s, then we're going to have 2 NH4s. Right? And so if we add 2 to either one of these, we'd have to add a 2 to the other to make sure the ends balance out. Right? So now let's count up our H's. We know that we've got the right number of SO4s because there's only 1 here and only 1 here. So let's just count up our H's. That's the only thing we got to figure out. 2 H's here, total of 6 H's here, so a combined total of 8 H's, and then 2 times 4 is 8, right? So we're all balanced. We're good. Does that make sense? Yep. Excellent. The way that some of you look away and don't want to make eye contact when I ask that question tells me a lot. Does that make sense? All right. See me after class if you got questions. That'll help you. All right. Let's do, let's see, is another example? Where are we? Yep. All right, so let me write down this equation. We're determining the chemical equation for acid-base reactions. All right, so we just did an example where we did that. Assuming again that the base only receives 1, we can make that assumption. Let's look at this chemical reaction. HF aqueous plus KOH aqueous yields H2O liquid plus KF aqueous. All right, so based on the rules, I'll let you write that down. Give you a moment. So based on the rules, yes.
Is this 11.13? I mean, 11.3.
This, as far as the problem, I'm not doing an example yet. No, this is just what I'm writing down. Yeah. This is just something that I'm showing you guys. So for this reaction here, based on the rules, the 3 rules that we just went over, we should be able to see very clearly which one's the acid and which one's the base, just looking at some of the things that are unique to each compound, right? So one of the things that we saw was that if it's a covalent compound that starts with an H, then it's most likely going to function as what? As an acid, right? And if it's an ionic compound that contains the hydroxide ion, it's going to be our base, right? So I'm glad that that one fits that description, because that's what we need for each of these reactions. We need an acid and we need a base. And it should make sense to us now why we have to have both, because it's getting rid of these hydrogen ions and something's got to take them, right? You can't have a reaction and they just disappear, right? We learned at the very beginning of the year that matter has to be conserved, and so it's got to go somewhere. Conservation of matter tells us that. So acid, this is the acid, this is the base, right? And this is a really common reaction here whenever you have an acid that combines with an ionic base, okay? When you have an acid that combines with an ionic base, you end up getting water and what we call a salt. And the salt, what is the chemical formula for salt, for table salt? NaCl. What kind of compound is it? Covalent or ionic? Heard some different. How do we know? What's our test? How do we know if something's ionic? Huh? Has a metal. So if we look at the periodic table, does that have a metal in it? Is it in the first 2 columns? Sodium?
Yeah.
It is, right? It's in column 1, right? So Na is a metal combined with Cl, which is a nonmetal, and so we have an ionic compound, right?
And covalent compounds are 2 non-metals.
2 nonmetals, that's right, yep. So if it's got a metal in it, we are assuming that it's an ionic compound. All right, so that's what our salt here is. When we say we take an acid and an ionic base, it combines together to form water and a salt. And what we mean by salt in that is it's an ionic compound, okay? We actually had a reaction earlier that I wrote down on the board that literally the compound on the end was salt. It was this reaction here, HCl plus NaOH yields H2O plus NaCl, right? So we have the same kind of scenarios, an acid plus a base, right? Covalent compound that begins with H, that's our acid. Ionic compound that has the hydroxide ion, that's clearly our base, and it produced water and salt. So this is a typical acid-base reaction with an ionic base. It produces water and a salt, okay? And so we're gonna make a note of that and make sure that you remember it. An acid reacts with an ionic base, and that's the key, with an ionic base to make water and a salt, right? It's not always NaCl, but it makes a salt. It makes an ionic compound, just like NaCl. And so we're going to do a couple of problems where you have this type of reaction, and it'll give you 2 compounds that you need to recognize which one's the acid, which one's the base. You need to recognize that the base is an ionic base. And so if that's the case, then you'll know that it's going to produce water, and then whatever the other compound is, it's got to be an ionic compound that's formed by whatever's left over once the hydrogen ion is donated. and accepted. Okay? So let's do one of those examples. And this is example 11.3 on page 337, and it says, what is the chemical equation for the reaction between HCl and CaOH OH2? All right. So we look at this. This is actually a really common acid. Does anybody know what acid that is? HCl?
We see it a lot.
Hydrochloric acid. Yeah, hydrochloric acid. And we recognize this as being, if this is the acid, then this has got to be the base. And really the base, remember in the order of the things, the base is the one that's the easiest one to identify first. Because those rules were more hard and fast, whereas the acid rule was kind of the last one that we bring in there. Right? Because we've already seen one covalent compound that begins with H, and it's not always an acid, and that's water. Right? We saw some reactions where H2O can also function as a base. So, but this one's clearly the base because it's got the hydroxide ion, and it's an ionic compound. So, what's it going to make? Well, we know then it's going to make water plus a salt, and we know the salt is whatever is going to be comprised of whatever compounds are left over from after the water's made. Right. So, what's going to make the water? Well, the H is going to be donated from HCl, and it's going to combine with the hydroxide ion to make water, right? So what's left over? Cl and Ca are left over. Does everybody see that? All right. CaCl is one of those a metal. Ca is a metal, right? What column is Ca in our periodic table? Is it column 1 or column 2?
Yeah, 2.
It's column 2, all right? So it's going to have a 2+ charge. What about Cl?
Column 7.
It's in column 7, right? So it's going to have a 1 negative charge. And so how do we know what ionic compound this is going to make? Well, we swap and draw, right? Which we've done several times now. So we've been doing that for several chapters now. So you should have this down. This is one of those things that if you don't have this down, it's time to get it down, right? It's too late to not. You should have known this a few chapters back because we keep doing this. You need to know this swap and drop process with forming ionic compounds or breaking them apart. Some of the things we do, we got to know how to break them apart. So CaCl2 is going to be our ionic compound, right? So that's our basic reaction. Acid and a base plus a water and a salt. Plus water and a salt. Now the only thing we have to do is make sure that our equation is balanced, right? So we count up everything. One thing that we see immediately is that we've got 2 Cl's over here, so we're going to have to put a 2 in front of this to balance our Cl's. And so now, if we count up our, well, we also see right here, we've got 2 O's, but we've only got 1 O here, so let's put a 2 in front of that. And so the only thing left to count up is our H's. Let's see where we stand with that. 2 H's here, 2 H's here for a total of 4 on the left side, and then 2 times 2 is 4 on the right side. So we're balanced with our H's also, so our equation's balanced. All right, and so just to kind of eliminate any fear for the equation balancing stuff. I mean, we had some more difficult equation balancing problems whenever we were initially learning how to balance equations, but the ones that we have with this are going to be pretty straightforward, just like this one. All right, they'll be pretty simple. Any questions about that? We're going to do one more problem that's basically the same. It's the same exact type of problem, but do you want me to go over anything else with this one? All right, so let's do the other one, which says, what is the chemical equation for the reaction between H3PO4 and KOH? Same exact type of problem. H3PO4 plus KOH. This is definitely our base. It's an ionic compound with the OH polyatomic ion in it, so that this has to be our acid, which makes sense because it's a covalent compound that begins with H. So it's going to make a water, not a water, it's going to make water, and it's going to make a salt. I keep saying that. It's going to make water and a salt. And so the water in these kind of reactions is always going to be made from the donated H and then the OH over in the other compound, right? So we're just looking at the ones that are left over, the PO4 and the K. All right, so K is our metal in this case. K, if we look in our book, is in column 1, so it's going to have a +1 charge. PO4 is a polyatomic ion, and if we look at the...
negative, I think.
Is it 3 negative? Yep, that's right, 3 negative. So we swap and drop to get K3 PO4. So K3 PO4 is our salt in this particular equation. So then we just got to balance it. We've got 3 Ks over here, so we know we're going to have to put a 3 in front of this K here. But when I do that, that gives me 3. We've got the same number of PO4s right here. So if we just focus on the O that's left here, the 3 in front of this gave us 3 O's. So let's put a 3 in front of this to make sure the O's match up. And so then it's just a matter of counting our H's, and we've got 3 H's here and 3 H's here for a total of 6, and 3 times 2 is 6 H's there. So everything matches up. And of course, you're welcome on the test if you want to actually list all of these out and count them up, you can do that. Just to make sure. That'd be enough. That if I was taking a test, I would probably do that just to be sure I didn't make a mistake. All right, list those out. So that's it. Any questions about acids and bases? How are we doing on time? What time is it?
I think it's 2:45.
Oh, perfect. I think my watch wasn't working today, so again, it's amazing. Just what a day, man. On target today. All right, everybody has their litmus paper, right? Everybody has their test. Is there anything else I was supposed to give you guys? I think that's it. All right. Have a great couple of weeks off, right?